Hi everyone, today I'm going to share the paper named Adaptive Response for Stochastic Synthesis. So I'm going to introduce it with four parts. So what's the text of the paper? So uh, what's the purpose of this paper? So the purpose of this paper is to distribute the power between multiple nodes in stochastic synthesis. Or you can say you are um, distributed running time between different trials. So the solution is mainly about modify looping sequence to search in parallel, and also they did a little bit um, optimism. They make some optimizations, but the most important is that they use Markov chains and they use geometric distributions to describe why their strategy can be useful. And also, they use these Markov models to explain why there are many plateaus during the search, which the plateau means that you can say your search algorithm finds nothing. It seems to be stuck in certain points where it did many meaningless attempts to open a new path to shorten to make the cost of current program less, but it failed. Their stochastic synthesis algorithm named adaptive restart strategy just as with its title side. In addition, they also provide us with a new benchmark using binaries from Ubuntu 16. So first, I'm going to introduce what is stochastic program synthesis. Stochastic program synthesis is that it focuses on if you're giving them a set of input-output pairs, then uh, they will, and you give them um, operation set to choose. You give them some opcodes. For example, like add, multiple, or subtract. You give them a set of OP code like operation code like add, multiple, or subtract, um, and you light the program to randomly search from the root to generate a program node tree like this, like this one. You can see that um, we can generate um, node tree like that. It means node X, node Y, and Z or Y. So one key attribute towards stochastic program synthesis is that it only focuses on the given set of input-output pairs, which means if you're first, if you give this input, then you must output the exact output. The second is that if you are not specify what output should be um, generated from this input, then um, Actually, different program can also be the answer of one stochastic program synthesis problem. So one problem can have multiple very different programs as answer. And here again, power means running time. We need to uh, know that since in this stochastic program synthesis, the state of one run means a trial means you start stochastic synthesis from a 0 point. Um, Power means that we need to know that since the uh, program state in one trail can be very small that we can memorize it. So we can also pass a run and then restart it. So the power means the overall running time, not you can, for example, if you assign a potential program with power 4, then uh, in the third iteration, then it this program can start to, for example, search 1 minute from this start point P, and then search another 1 minute and find still the P is best solution, and then they search another 2 minutes, but 1 plus 1 plus 2 equals 4. So it's overall running time, not the uh, single phrase of the search. In this text, to analyze the simple, it's a distribution of of um, running time, and to analyze the plateau generated in the running time, uh, in the program synthesis, we need to the article only focus on really simple programs. So first, it is very short programs. It only contains 3 to 16 instructions. So actually, I don't think it is just a simple function. And even if we print a hello world, it contains more than 16 instructions. And second, the generated program is a straight line. It means it is not without any for or while or go to or if sentence. Third, the general, of course, without try catch. And third, the generated program do not contain any I, I/O or memory related operation or any specialized hardware related operation. The first, the generated program, of course, need to be deterministic. It means it cannot contain anything, any core to random function, and it also need to free of side effects. We can say I/O operation or memory related operation as may carry some of the side effects. As we can see, the solution is based on two assumptions. First, we know that during the searching process, during the searching run, the longer searching time, the the further the search goes, the harder it is. So as we can see, there are actually many plateaus during the search. In the plateau, it seems the algorithm tries different kind of moves, try to fill in different kind of arguments, but it failed to reach better result. So it seems it just stuck there. But in a plateau, you need to give it enough running time so it can jump out of the plateau, so it can go to the further logic, or maybe it can also prove that this plateau, the challenge behind this plateau is useless. It just self-grouping. So the time is just waste. So the start strategy is actually used to help the search jump out of those plateaus, especially out of those, especially the restart strategy is especially helpful when the plateau is useless. So it is not necessary to go through that plateaus. And second, the second assumption is that the distribution of time spent is usually a heavy tail distribution. It is also uh, under the same uh, actual observation. That means the longer you search, the harder your algorithm will fail. Um, in that case, uh, the in a heavy-tailed distribution, and the restart strategy can show an overall improvement in the searching speed. But the restart strategy can actually damage the performance in non-heavy in this in running time distribution that is not actually a heavy-tailed distribution. So to understand the adaptive restart solution strategy, you first need to understand the Ruby sequence. It is published in 1992. Its title is Optimal Speed Up of Las Vegas. Las Vegas. Las Vegas. Las Vegas. Las Vegas. Las Vegas. Optimal speed up of Las Vegas algorithm. So it is actually similar to the adaptive restart strategy. It is also try to distribute running time, distribute power between runs in Las Vegas, stochastic searching to accelerate the whole searching process. Actually, it has a rather straightforward solution. That means if you are giving, so you must make sure that one time unit can uh, are larger than the minimum time required uh, for the search. Then you first run one unit time, and then you run another one unit time, another 2 unit time. You can uh, you can find that it is actually the similar to a binary tree where you can separate it into different segments. Each segment, each segment has a prefix of the the following segments. So actually, we first need to know what is Las, Ve- Las Vegas algorithm. It is actually in short, it is a randomized algorithm that using tree search. In short, that is stochastic tree search program with and you can always produce a correct answer when it stops, but the running time is a random variable. Sometimes the running time can be infinity. We consider the problem of minimize the expected time required. The as the aim of the Ruby sequence. So Ruby sequence actually is very simple. It just runs the algorithm for time ti, time distributed until the time is run out. Then it starts from a clear state. It do not need to pause or remember any difficult states or distribute it between different coast. It just run a certain time and stops. Um, So what's the contribution of such a paper? So in the Ruby sequence paper, we first consider a well-known distributed P distribute, or where we first handle dealing with the situation that we know the details about the distribution P. Then if we can find a optimum t time t, then we can always use a sequence of t optimal t as a cutoff, which means we run t optimal and then or t star, and then after t start unit time, we just stop the uh, stop the program and restart the searching until it produces a correct answer. Here we must know that T star must be uh, longer than the minimum possible running time required by the search. So, for example, if you are running the program synthesis, then you need to, for example, synthesis a 3 instruction long program, then T star must be longer than uh, randomly select three instructions and combine them together and output. So first, the Ruby sequence, the paper proves that using such strategy is optimum, uh, even if we consider a mixed strategy. In the mixed strategy, we allow a run to be restarted after being paused. And the second part of the paper also said, which is used by the paper by the adaptive restart. It produce it is when dealing with a distribution too complex to know. It gives a universal strategy that we can see the same sequence as before. The paper proves that the university strategy can always have a upper bound, and this running time upper bound on running time, and this upper bound on running time is a reasonable uh, upper bound for all solution, all strategy, all simple strategies. So the universal strategy is close to optimum strategy, and we can use it. This Ruby sequence, um, it is close to one of the lower bound of all the upper bound on the running time of any policy. I forgot the keyword, the term of the lower bound of all upper bound of any policy. So Ruby sequence has been or the restart strategy has been applied in many different aspects in many fields. One of them is SAT solver. SAT problem. We first make a brief introduction about SAT problem. It means you need to determine whether variables of a given Boolean formula can be consistently replaced by true or false. It means whether you can assign each variable a true or false, so the entire formula can always be true. For example, to satisfy A and not B, you can use A equals to true. True here we donate with 1 and B with false. But some of the formula can never be satisfiable. For example, A and not A. In such case, the expected running time can be infinity. Oh, no. It's not infinity. It's just you need to go through all of the combination of true and false. So, how can we apply restart um, with SAT problem? You just clear all learned variables and backtrack to the root to um, re to uh, try to solve the problem from beginning. So in order to understand SAT solver carried with restart strategy, we need to begin with DPLL, Davis Putman Login Loveland algorithm. It's just a straightforward uh, deep deep first search algorithm. And here you can see the unit propagate. Unit propagate means that if you already know that you need to assign a if there are a and B, you know A is a unit clause and B is also a unit clause, and you need to assign A with 4 is true. So you replace A with true and you separated, distributed this message to all of the subclauses. Another thing is pure literal sign. Pure literal is what is a pure literal? Pure literal means that it is actually similar to unit clause. Pure literal means that you say all of the clause when, for example, for a variable a, all of the positions that a shows, it requires a to be true. You never say a vowels a prefix not. Then you know a needs to be true. Then you replace a with true. Sometimes you also say not b, not b, not b. You know that b will always be false. It is just a simplified uh, deep first searching. You try uh, you randomly select literal L. You first try whether literal L can be true, then you try whether it can be false. So it gives us a question: how can we select which L to be used, and how can we select? How can we use use a failure search? So we have CDCL, conflict driving clause learning. It for example it comes from that idea. If set A uh, if set A belongs to set B, then B's complement belongs to A's complement. That is obvious. So if we can so when we found uh, conflicts in DPLL, we found that we can there are still conflict clauses we fail to solve this. We can just um, memorize this conflict into our search experience and use, and we can actually jump back to the first conflict variables to resolve the partial problem. Obviously, that you need to uh, waste time as the search goes. You will accumulate too much conflicts. The conflict itself will, in fact, affect the result of search. It can affect the complete of the search. It when you are accumulate too much conflicts, which keeps jump to the first country conflict variables, and it will actually slow down the whole algorithm. So the results in CDC algorithm is that uh, if you're running and you're collecting TL conflicts, then you just stop the algorithm and you start it with a clear conflict set from the beginning. So we can also find a paper named Verified SAT Solver Framework with Learn, Get, Restart, and Incrementality that it can show the relationship between different strategies. We can see that CDCL can usually learn, uh, use with a restart strategy, and when the restart strategy is used after M steps, Fn step, where F is actually the Ruby sequence. After F steps, uh, then the whole uh, then the whole learned clauses are just forget. Forget and they start with a clear state. The paper is also based on stochastic superoptimization that published in SPLOS 20 and 30. Here, the paper is meaning uh, about super optimize the loop-free binaries. In this paper, they turn the um, turn they need to um, turn the unoptimized binaries into a program with same output and uh, but with a faster speed. So it is kindly similar to the synthesis program, but it also has a performance requirements. In this paper, they turn the usually it is solved by some expert solution, but in this paper, they turn the optimization process into a stochastic search with Markov chain and Monte Carlo samplers to synthesis part of the uh, optimized program from scratch. Not from scratch, but similar to that. So the interesting part is that first it used Markov chain. Second, it used a special designed cost function which combines the competing constraints of transformation correctness. That means you need to output the similar or the same, not just similar, the same output. And it also combines the performance improvement. You can see that here is the correctness part and here is the performance part. Uh, the work contain there contains four types of work, which is very similar to this paper. Also, first you can choose operation code and replace it. You can also choose operand, or you can swap two lines of code, and you can also swap. Um, you can also replace instruction with uh, with a random instruction that do not cause loops. So in order to provide enough transformation correctness, they actually divide the learning into two phrases. The first phrase is called synthesis. It focuses on correctness. It focuses on the uh, first, the focus on the weight of correctness. The second part is called optimization. So in this step, the generated program is already correct enough that can output similar output. It can generate similar output as the original uh, optimized programs. So the second phrase of my cost minimization can focus on finding the fastest program. So that's the background and related work of this restart adaptive restart strategy. Here, we are going to introduce the design and the algorithm of this paper. So first, we need to introduce the stochastic synthesis algorithm used in the adaptive restart strategy. The algorithm actually it fits a simplified problem that contains much simpler operation codes and much simpler input-output relationship. The algorithm always starts from zero state. It only contains one instruction node named zero, and in each step, it maintains the current program P and propose and generate a possible program P plus. In each step is randomly select one of the movements. The movement our introduction later. So if the generated program have a lower cost, then then we will accept the generated program and we will discuss the original program P and keep P plus in the memory and report P plus at the end of the search. But if the cost of P plus is actually larger than the cost of P, we also need to accept it at a certain rate since sometimes you need to, for example, you need to make a large change on the program structure. You must go through some little higher you must go to some intermediate program state with little higher cost. Then you need to introduce. You need to do that. In this function, they introduce a variable named beta. Beta is beta is proportional to the probability of accepting a solution that is not optimal. So the movement contains three types of the movement. The first type is select a instruction and randomly fill the op the operation codes and the argument required by the operation codes. And the third and the second and the third movement are the similar. Randomly choose a operation code and replace it with another operation code with the same arity. Here the article use three types of cost functions. The first is Hamming code, and it also uses incorrect test case, the number of incorrect test case, and difference of the three cost functions are proved to be valid and can be helpful with adaptive restart strategy. We need to specify beta. Beta, we design that so the beta conforms to exponential distribution, which means that uh, actually I didn't get it in the paper, but I think I have understand the essential meaning of beta, which means that if you're for example, when beta is equals to 1, then the higher the cost is, the lower the the probability of accept is. So with a cost of 3 bits, you got accept rate of 5%, but when the cost is 6 bit, you only get it uh, 0.20 25 5%. Actually, beta can be very large. It can be larger than 20. Uh, the article also did a little research on the optimum value of beta. Here, the in order to prove the, in order to give an explanation on the adaptive restart strategy, the straightforward strategy in the article. The article actually uses a very simple example that only contains 8 of opt, operation codes, and it only contains 35 popular states to build a Markov chain to imitate the transition between different states, and we can say that there is a strongly connected component in the center of the not center but in the center of the uh, in the center of the synthesis progress. So in that components, we can actually cause a plateau, because if you are you can your search can easily jump into the strongly connected components, but you can not able to jump out of the components since the probability of slow self looping is actually larger than the probability uh, of jump to the solution node. And second, uh, in the second observation is that the restart strategy can accelerate the searching when there is a low cost, strongly connected component, which is not means the a component at the center, but it means the component at the right at the right left uh, at the right upper corner. There is a relatively more strongly connected component, and it has a low cost. So when the search enters to this strongly connected component, it cannot easily jump out of it. In the meanwhile, it is not uh, on the necessary path. So if our search jump into that component, we can just stop the search and restart the overall search. So maybe the next time the start, we can avoid this right upper corner component to accelerate the whole searching. And second is that when beta is large, then the Gaussian row of the cost function is vacant. That is because the probability of acceptance is high uh, without um, and the algorithm will behave just like the random walk algorithm in like the function the algorithm used in the early Google. So here is the optimum uh, beta in different under different cost function and different strategy, and the beta can be really high. So the K analysis to this problem is that you need to use is when there are such kind of strong components uh, in the program in the code logics or in the distribution of the program, then that if you have a single dominant strongly connected components, you can view the distribution as a geometry distribution. And in geometry distribution, and in geometry distribution with a high beta, restart strategy is not optimal. But if you have multiple dominant strongly connected components, and each path has one dominant strongly connected components with similar distribution, then the whole distribution is just a sum of geometry distribution. And in that case, if some of the some of the paths must be necessary to restart. It will cause heavy tailed distribution. If it causes heavy tailed distribution, then the restart strategy can be helpful, which is it is what I came up with, not mentioned in the paper actually. So with similar distribution, then the paper think it will be gamma distribution. But if there are the distribution of those strong components can be too different, then they will view as a normal distribution. So of course, if there are only one key path and you must spend time on that key path to pass it, then the restart strategy is actually detrimental since if you restart, then the time you spend on break through that path is waste. So the above the since that mentioned above is some kind of analyzing for the probability distributions uh, on the program synthesis. After that, it's the major design of the adaptive restarts. We can see that we can view the adaptive restart as a Ruby policy that actually records the cost function and low passes. We need to mention that in the original Ruby policy, pauses is can be allowed, but it's not necessary. So, in the original Ruby sequence, we can view the Ruby sequence as a binary tree. In the adaptive restart strategies, um, instead of using the instead of, for example, instead of root uh, add a root 8 and add another duplicate of current tree at the left at the right child of the root. The adaptive restart choose to run twice of the time on on each on each node. Then it gives each leaf node some small leaves. Those leaves, you can see that instead of from A to C, it first multiple all of the uh, provided running time on the nodes, and then it add a lot of leaf nodes with a running time of just allowing 1 unit time. So that's the algorithm of adaptive result. You can see that first it is very simple. First it doubles the first it handles the left child and then it handles the right child uh, to update the cost of its child to separate the cost function. And after that, it doubles the running time of the current node in the seventh sentence. And we need to mention that the adaptive restart strategy introduced the cost function into the Ruby function. So if the cost of child is actually lower than the cost of parent, then the program of child will be swamped with the program of the parent. So since the parent always have been distributed with more time, so we need to run the cheaper program with a longer time, so we swamp the program. Here is an example that the adaptive restart actually performs worse than the Ruby policy. For example, uh, if immediate strongly connected components um, has a has a lower cost, while uh, it has a um, lower probability to jump to the final solution, which means the cost function do not necessarily uh, the guidance role of the cost function is damaged. In such cases, the adaptive restart strategy performs worse than the Ruby policy. It also construct a benchmark. So the algorithm is very simple. We will just skip that. The evaluation contains three different kind of cost function with two data set, and they also did some additional research on the effect of beta. Here are some questions, questions remain. Questions.